Yes, my dear students, let us go to the next part of the discussion in states of matter. We are doing some numericals in states of matter. In numericals, as of now I gave you two numericals here where you need to focus. One is air contains 23% and 77% of nitrogen, 23% of helium and 77% of nitrogen by weight. The percentage of O2 by volume is actually this is 23% of O2. Air contains 23% of O2 and 77% of nitrogen by weight. The percentage of O2 by volume is. So how do you approach this problem? So here what we can do here is, that is simply you take here for the first one we can take 23 grams of O2 definitely contains 22, that is 32 grams of O2 at STP contains, that is 22.4 liters, then again 23 grams of O2 contains how much? X is equal to question mark. So here you can take X is equal to 23 into 22.4 divided by 32 grams, 32 liters. This is 32 liters. Keep it like that. Again, second one is, if you are going for nitrogen, 77% is saying. So molecular weight of nitrogen is 22.4 liters. So 77 grams of nitrogen at STP would occupy how many liters? Let this be Y liters. So that means here you can take Y is equal to 77 into 22.4 divided by 28 liters. So if you want exactly the percentage by volume means you can take here, that is if you want the, because it is asking the percentage of volume of oxygen. So if you want to take the percentage of volume of O2 is equal to X by X plus Y into 100. You do it and definitely you are going to get, that is 20.7 will be the correct option. Option B is the correct option. After simplifying, percentage of oxygen is going to be 20.7. Percentage of O2 by volume you can obtain it. Now go for the second case of the question. A gaseous mixture contains 50% of helium and 50% of methane by volume. Calculate the percentage by weight of methane in the mixture. That means what we need to understand here is, if you go for the second case hint I would like to give you. In the second case hint, that is you take two gases, one is helium and the other one is methane. Both are 50% is to 50%, means 1:1 ratio. This is volume ratio. This has to be a volume ratio. I can write here, this is volume ratio. So if this is volume ratio, then how many parts of volume is present in the helium is, because ultimately it is asking the percentage by weight of methane in the mixture. So if you go for helium the volume parts is 1/2 and for methane also it is 1/2. 1/2 means this is going to be, this is mole ratio, let us take this as mole ratio. So 0.5 mole is to 0.5 mole. This is because in mole concept we have one condition. So I am writing here one important condition I would like to write. Hint, I would like to put it like this. Assuming number of volumes is equal to number of moles. Assuming number of volumes is equal to number of moles. So though we got volumes, these volumes are being assumed as number of moles. So we got 0.5 mole of methane. So we got 0.5 mole of methane. From 50% of methane we got 0.5 mole. So 1 mole of methane contains 16 grams. So 0.5 mole of methane corresponds to, that is 8 grams. 8 grams we are going to get. If it is 8 grams, then similarly 1 mole of that is the next gas is helium. 1 mole of helium contains 4 grams. So 0.5 moles of helium contains how much? This is 0.5 into 4, this is 2 grams. So because he is asking us to calculate the percentage by weight of methane in the mixture. Percentage by weight of methane in the mixture means percentage by weight of methane in the mixture is 8 grams. So I can take that step as percentage by weight of methane in the mixture is equal to 8 by 2 plus 8 into 100. So this is going to be 8 by 10 into 100, which is equal to 80%. So approximately we are going to get option D is the correct answer. So fourth option is correct. So second problem, fourth option is correct, and that is the calculation for the second numerical. And this is the important hint I would like to give you. Assuming the number of volumes is equal to number of moles, we got 80%. Yes, my dear students, let us continue the numericals. Two more problems I gave you here. Here in the first case, a certain gas diffuses from two different vessels A and B. The vessel A, two different vessels A and B. The vessel A has circular orifice while vessel B has a square orifice. That means two different vessels are there, one is circular orifice and the other one is square orifice, and the ratio of the rates of diffusion of the gases from vessel A to B, assuming the temperature and pressure to remain constant. That means this problem is basically from the topic of Graham's law of diffusion. So based on, I am putting in this way, based on Graham's law of diffusion. Based on the Graham's law of diffusion, we have rate of diffusion is directly proportional to that is orifice. Rate of diffusion is directly proportional to shape of the orifice, nature of orifice. What is orifice here? In one case we are saying square orifice and in another case we are saying circular orifice. In one case we are saying square orifice and the other one is circular orifice we are saying. If it is circular orifice, then you can take, this is a circle, a small hole is created, and this is the escape of gas molecules, escape of gases takes place. If it is square orifice, this is the square orifice, this is the square orifice, and this is circular orifice. Okay. So based on this, directly I am going to take here rate of diffusion of the circular orifice, rate of diffusion of A divided by rate of diffusion of B is equal to orifice of spherical orifice, circular orifice. Okay, I will put it like this: area of circular orifice, divided by area of square orifice. So area of the circular orifice, we know it is pi r square, and area of the square orifice, we know it is r square. Area of the square orifice is r square and area of the circular orifice is pi r square. So r square gets cancelled. So finally you are going to get pi by 1. Pi by 1 means you can select the best option. These are the options available here. These are the options. So we can go with the first option because we got pi by 1 as the answer. So that is about the third numerical. Now let us go back to the fourth numerical. If you are going to the fourth numerical, two glass bulbs A and B are connected by a very small tube having a stopcock. So suppose these are the two glass bulbs. Imagine that this is the first glass bulb, okay, and the one is second glass bulb. This is glass bulb A, glass bulb B, having a stopcock. Stopcock means you can just use the stopcock over here. Stopcock, and bulb A has a volume of 100 centimeter cube. This is the volume in the bulb A, while the bulb B is empty, is saying So if that is the case, opening the stopcock, the pressure fell down to, that is 40%. What could be the volume of the bulb? What could be the volume of the bulb B could have been after opening the, volume present in the bulb A. So I think you can use P1, V1 is equal to P2, V2. Initially, because he is saying that the pressure has fell down to 40%, means let P1 be equal to 100. You can take 100 centimeter into volume you can take initially 100. Now pressure fell down to 40. So P2, let us take it as 40. Let the volume, the final volume be equal to, that is, you can take pressure. So here pressure and initial pressure and initial volume is 100 centimeters of pressure and 100 centimeter cube of the initial volume. Final pressure is P2 is 40 centimeters. So final volume is how much? So this is going to become 0 gets cancelled, 1000 divided by 4, which is equal to 250 centimeters cube. But he is asking the volume of the bulb that must be. Volume of the bulb that must be means actually what is the exact amount of the volume which has entered into the bulb B from bulb A. So what we have to do here, because we got the final volume as 250, so that means the volume of the bulb B. Now volume of bulb B is equal to V2 minus V1. V2 minus V1 means 250 minus, initially it is 100. So this is going to become 150 centimeter cube. Because the pressure has reduced to 40%, the volume proportionally it has increased to 250 centimeter cube. So what is the exact amount of volume which has entered into the bulb B, which was initially empty, means that is 250 minus 100 will give you 150 centimeter cube is the exact amount of volume which has entered into the bulb B. So therefore 150 centimeters means option C is the correct answer. Yes, my dear students, please look at this problem here. We are just continuing the next problem. We have done 4 numericals and this is the 5th numerical and the 6th numerical. Let us see what exactly we are trying to approach for these 2 problems. Actually, if you go to the 5th numerical, he says the RMS velocity of hydrogen is root 7 times the RMS velocity of nitrogen. If T is the temperature of the gas, then that means sometimes when you are solving numericals, you should also look into the options. You should use little bit of common sense, and if you look into the options, he is trying to compare the given data, whatever he has given, he is trying to compare the temperatures of the nitrogen gas as well as hydrogen gas. So through what method, if you are going to approach, we can get the correct option in this problem, we have to see. So we all know that RMS velocity, if you take, what is the formula for RMS velocity? RMS velocity is equal to under root of 3 RT by M is what we can take. Here it is very clear that the gases are different. There are 2 gases. Well, the first approach is RMS velocity is equal to under root of 3 RT by M, where R is the gas constant and T is the temperature and M is the molecular weight of the gas, C is the RMS velocity. But because gases are different, there are 2 gases. One gas is hydrogen and the other gas is, that is, nitrogen. So 2 gases are there. So that's why what I am going to do here is, I am going to directly blindly I am going to equate this. See, RMS velocity of hydrogen divided by RMS velocity of nitrogen. RMS velocity of nitrogen is equal to under root of 3 RT, temperature of hydrogen, divided by molecular weight of hydrogen, we know it is 2 grams. Directly we can substitute. Again under root of, that is 3 R, temperature of nitrogen, divided by molecular weight of nitrogen also we know. But in the meantime, he says clearly the RMS velocity of hydrogen is root 7 times the RMS velocity of nitrogen. So what I will do here is, I can take this step as, again next step, this is root 7 times the RMS velocity of hydrogen is equal to root 7 times the RMS velocity of nitrogen into RMS velocity of nitrogen divided by RMS velocity of nitrogen is equal to this root gets cancelled, 3R also gets cancelled. So this is going to be temperature of hydrogen divided by 2 divided by temperature of nitrogen divided by 28. That means that same step, if I want to repeat, this step is going to get cancelled. So next step you can take here root 7 is equal to, this is nothing but, you can take here 2 ones are 2 14s are, so 14 will come to the numerator. So 14 into temperature of hydrogen divided by temperature of nitrogen. Temperature of nitrogen. So what we are able to understand here is, that is, if I take temperature of nitrogen is equal to 14 into temperature of hydrogen divided by root 7. That means it is very clear that, very clear that definitely from this data it is very clear that temperature of nitrogen is definitely greater than temperature of hydrogen. By how many times? By 14 by root 7 times the temperature of nitrogen is greater than temperature of hydrogen. So by looking at the data you can easily understand. So we can say that option C is correct in this problem. Look at this. Go to the problem number 6. What we are trying to say here is, this is problem number 5, solution for problem number 5. Hint for numerical 5. Now I am giving you hint for numerical, that is 6. So because he is asking in the options, because he is already mentioning the compressibility factor, directly we can apply the formula of the compressibility factor, that is compressibility factor is equal to PV by, that is RT. Anyhow carbon dioxide is 1 mole, so directly we can take PV, pressure into volume divided by gas constant into temperature. If you are going to take, yes, temperature is given, pressure is given, then volume is also given. I think if you substitute you can get the answer. Pressure is around 40 atmospheres and volume is 0.4 divided by, because both pressure and volume, both of them they are expressed in, that is atmospheres and liters, we can take the gas constant as 0.0821 into temperature is 300. So this step is going to become 16 divided by, I think I can take this as 22.4 divided by 273. If I take into 300, if I am taking, I think still we can cancel it. When we are cancelling it, or else I can do one thing, you can just cancel it like this, 100, 3 tens are 300s are 300 and 9s, this is 1s, and this is what you can do, or you can just go for the another type of simplification. This is 16 divided by, I will approximate the 0.0821 as 0.08. If I take 0.08 in the denominator, this is 0.08 into 300. If I take, this is 16 divided by 24. 16 divided by 24 means numerator is lesser value and denominator is higher value. So this is 4 4s are 4 6 means 2 by 3. 2 by 3 means 0.6667. That means here it is a clear indication after calculation. After calculation, z value is less than 1 because it is only 0.67. So you can come to the conclusion that z value is 0.67 means the compressibility factor is less than 1. Less than 1 means it is the gases are more compressible. That means carbon dioxide gas now, because the compressibility factor is less than 1, carbon dioxide is more compressible gas, more compressible gas, and also it is highly liquefiable gas, highly liquefiable gas. My dear students, let us go to the next numerical, next two numericals, that is 7th and 8th numerical in states of matter. Look at the 7th numerical what I gave you. Pure O2 diffuses through an aperture in 224 seconds, whereas a mixture of O2 and another gas containing 80% of O2 diffuses in 234 seconds. What is the molecular weight of the gas? So what we can do here is, the best thing what we can do here is, like there are two gases actually. One is, there are two gases. If you are going for the, that is 7th one, hint, let us go like this, that is one is O2 gas and the other one is, that is one is O2 gas and the other one is gas X. You can take gas X or gas M. M is the gas, unknown gas. So here O2 is 80%. If O2 is 80%, then what we can do here is, we can take 80% of O2 and 20% of the gas is what we have here. So therefore the best thing what you can do is, here the molecular weight of O2 we know, that is 32, and the molecular weight of gas X is m grams. So what I can do here is, molecular weight of the mixture is equal to 80 into 32 plus 80 into 32 plus 20 into m divided by 100 we are going to get. So this is one step which you need to keep it in your mind. Then after this, that means this m is the molecular weight of the unknown gas, that we can calculate in the last step. In the meantime, he is saying that, and what is that he is adding? He is saying that the pure O2 diffuses through an aperture. Aperture means it's a small space. Aperture means you can take a small balloon like thing. This is a small balloon, and in which if you punch a hole, okay, you can see that the gas keeps escaping out. That's an aperture. Aperture is a small pinhole where in which the gas keeps leaking out. Okay, so pure O2 diffuses through an aperture in 224 seconds, whereas a mixture of O2 and another gas containing 80% of O2 diffuses in 234 seconds. So here you should be little bit careful. So what we have to do here is, now what I am doing here is, I am taking it like this, rate of diffusion of O2 divided by rate of diffusion of the, because he is saying that when one case pure O2 diffuses through an aperture of in 224 seconds, whereas a mixture of O2 and another gas containing 80% of O2 diffuses in 234 seconds. So that's why we are taking rate of diffusion of the mixture and is equal to, you can take this as volume of O2 divided by volume of O2 divided by time of O2 divided by, you can just take proportionality, or else you can just take the proportionality. Similarly, volume of the mixture divided by time of the mixture is equal to under root of molecular weight of the gas m, because we don't know what is the mixture molecular weight m, divided by, you can take here, that is molecular weight of the oxygen gas. So what we can do here is, because anyhow in both the cases he did not mention anything about the volume, he did not speak anything about the volume, but he just spoke only about the time here, 224 seconds and 234 seconds only he spoke, but volume he did not mention. So that's why what I will do here is, volume of the oxygen gas and volume of the mixture I am cancelling. Now therefore this step is going to become what? This is time of the mixture divided by time of diffusion of the mixture divided by time of O2 is equal to under root of molecular weight of unknown gas m divided by molecular weight of oxygen is 32. So that means here you can substitute both these values. For O2 it is 224 seconds, and for O2 as well as mixture it is 234 seconds. So this step again we can go back to this step as O2 of the mixture is 234 divided by, you can take divided by, that is time of oxygen, it is 224 seconds is equal to under root of molecular weight of the gas m divided by 32. So now the molecular weight of the gas, that is unknown gas, after calculating this step, we get almost molecular weight of gas m is equal to 39.42 approximately I am giving you. So this 39.42 you have to substitute, okay, this 39.42 m you have to substitute in the mixture. Here you have to substitute, because finally what is the molecular weight of the gas is asking. Okay. So here what is happening here is, just this is molecular weight of the mixture you write here, just you take it as molecular weight of the mixture, here also molecular weight of the mixture. So here also you are going to get molecular weight of the mixture. So molecular weight of the mixture means this value you can substitute over here. If you are substituting, this is nothing but this step is going to be 39.42 approximately. If you substitute, this is 80 into 32, 80 into 32 plus 20 into molecular weight of the unknown gas. M is the molecular weight of the unknown gas divided by 100. Then after calculating that value, I think approximately we can get, so approximately after calculating this value, approximately we are going to get, that is 46.6 grams will be the final answer for that calculation. So we can go directly and take the third option as the correct option. Now let us go back to the 8th question. So this is a hint of the 7th question. Let us go back to the 8th numerical. In the 8th numerical, what we are taking is taking 20 grams of chunk of dry ice. Dry ice is nothing but solid carbon dioxide. This is nothing but dry ice is nothing but solid carbon dioxide. 20 grams of chunk of dry ice is placed in an empty vessel of 0.75 liters is the empty vessel. Bottle is tightly closed. What would be the final pressure in the bottle after all the carbon dioxide has been evaporated and the temperature has reached 25 degrees centigrade? So what we have to do here is you can directly apply the formula pressure is equal to pressure into volume is equal to, because he already gave weight of the carbon dioxide. So I am taking N into R into T. Apply the ideal gas equation. If you apply the ideal gas equation, pressure that's what we are calculating. Pressure we have to calculate into volume is 0.75 liters is equal to weight of dry ice is 20, molecular weight is 40 into 0.0821 into temperature is approximately where is the temperature, how much he gave, 25 degrees centigrade temperature he gave. 25 degrees centigrade means it is 298. So 298 Kelvin. So after simplifying this step, we are going to get pressure calculated is equal to 14.828 atmosphere. But already I gave you one hint here. So the final pressure which we are calculating, therefore pressure final pressure is equal to, that is calculated is 14.828, and pressure of the atmosphere is constant in atmospheres, that is 1 atmosphere. So therefore this is going to become 15.828 atmospheres is what we get finally after calculating the problem, because when you are opening it's like 20 grams of the chunk of dry ice is placed in an empty vessel of 0.75 liters, bottle is tightly closed. What will be the final pressure in the bottle after all the carbon dioxide has been evaporated and the temperature has reached to 25 degrees centigrade? Means you are just opening the closely fetched, the stopper is tightly packed. Once you open the stopper, all the compressed carbon dioxide goes out. So when the compressed carbon dioxide is going out, that excess pressure whatever you got, calculated pressure is 14.828 atmospheres, but apart from 14.828 atmospheric pressure also we have to add. That atmospheric pressure is 1 atmosphere and calculated pressure is 14.828. So total it is 15.828 atmospheres is the final pressure which we are calculating for the tightly closed bottle whose volume is 0.75 liters. So I can go with that is first option, that is 15.828 atmospheres is the final answer for this problem. Look at this problem, that is problem number 9. An open vessel containing a gas at 27 degrees centigrade is heated to 927 degrees centigrade. What is the fraction of initial mass of the gas which escapes out? So here this is one problem, and another one is a 1.12 liter flask containing oxygen is partially evacuated till the pressure falls to 7.6 into 10 to the power of minus 10 millimeters at 0 degrees centigrade. Calculate the number of molecules present in the flask. So two problems I gave you. So first problem let us try to approach. In the first problem, what we can do here is he himself is saying that the vessel is open vessel. So ninth one hint. When I am going for ninth one hint, he is saying that the gas is open vessel. It's an open vessel. Inside it is being filled with gas. This is gas. And he is saying that initially the vessel temperature T1 is 27 degrees centigrade, means you can take 300 Kelvin is the initial temperature. Now from T1, now it is being heated up to temperature T2, which is equal to 927 degrees centigrade, means which is equal to 1200 Kelvin. Okay. In the problem nothing is given, he is not mentioning anything about, that means this problem is basically based on the ideal gas equation. Pressure is equal to PV is equal to pressure into volume is equal to N into R into T. He is not speaking anything about the pressure, so I am cancelling the pressure. He is not speaking, R is anyhow constant, so I am cancelling even the universal gas constant also. He is not speaking anything about volume, so I am cancelling even volume also. So N into T is the constant, that means number of moles and temperature is constant. So therefore N into T is equal to constant, but number of moles is nothing but W into the weight by gram molecular weight. Weight by gram molecular weight into temperature is again constant. That means what we can do here is, because he is asking very clearly what is the fraction of the initial mass which is being escaped out. That means what I am doing here, let the initial mass initial mass is equal to W1 grams. Let the initial mass be W1 grams. So what I am going to do here is W1 into T1 is equal to W2 into T2. Let us take it like this. Let the W1 grams, okay, W1 into T1 is 300 Kelvin is equal to W2 into 1200 Kelvin. So W2, so 2 zeros gets cancelled, 3 ones are, 3 fours are. So W2 is equal to W1 by 4 is what? The gas which is remaining in the vessel. But he is asking how much amount of gas has been expelled out. Escaping is nothing but expelled out. So this W1 by 4 is the amount of gas remains in vessel. Then what is the gas which is expelled? The gas which is expelled, that is leaked out. So gas expelled is nothing but W1 minus W1 by 4, which is equal to 3 by 4 of W1. So therefore 3 by 4 of W1 is the answer, means option A, first option is correct. 3 by 4 is the amount of gas which is expelled. Now going back to, that is the 10th one, 1.12 liters of the flask containing oxygen is partially evacuated till the pressure falls to 7.6 into 10 to the power of minus 2 millimeters at 0 degree centigrade. Calculate the number of molecules in the flask. So what we can do here is, the best thing what we can do here is, I have little bit space over here, I will utilize this space because majority of the space has been utilized only for solving problem number 9. Now problem number 10, here also I am going to apply pressure into volume is equal to N into R into T. Pressure he gave 7.6 into 10 to the power of minus 10. Yes, my dear students, here let us go to the 10th question. As already I told you, hint 10th one, 10th hint. If I take pressure into volume is equal to number of moles into universal gas constant into temperature. So pressure, if it is expressed in millimeters, divide with 760 so that we can get the atmospheres, or else I am writing the units also, into volume 1.12 liters. So 1.12 liters is equal to number of moles we have to calculate, because ultimately is asking number of moles, number of molecules is asking. So if you calculate the number of moles, you can calculate the number of molecules, because 1 mole contains Avogadro number of molecules. So calculated number of moles, if you equate, you will get number of molecules. So what I will do here is, I will take this N as it is, R value I am taking 0.0821 liter atmospheres per mole per Kelvin into temperature. Temperature is how much? 273 Kelvin. So in Kelvin inverse, Kelvin gets cancelled, then liter atmospheres and liter atmospheres also gets cancelled. So only mole is remaining now. Yeah, that anyhow we are going to get moles, no doubt about it. So here this is going to be, this is 76 by 76 into 10 to the power of minus 12 is equal to N into, this I will write it as 0.0821, I can write it as 22.4 divided by 273 into 273 of mole inverse. 273 also gets cancelled. So this value, number of moles, N is equal to, you are going to get some value, you are going to get that this 76 into 10 to the power of minus 12 divided by 22.4 into 76, and 76 already gets cancelled, into 1 by 76, it gets cancelled. Okay. So this is going to become 10 to the power of minus 12 divided by 22.4 moles. Because he is asking number of molecules, just what you have to do is, this 10 to the power of minus 12 divided by 22.4 into 6.023 into 10 to the power of 23. Upon simplification, you are going to get 3 into 10 to the power of 10 molecules. would be the answer, final answer. So, therefore, this is third option is correct, 3 into 10 to the power of 10 is correct. Yes, my dear students, look at these two problems here. One is you can go for 11th and the other one is 12th problem. So, 11th problem, if I am taking the hint, 11th hint, if I take at constant temperature, if the pressure increases by 1%, the percentage of decrease in the volume is, that means this 11th problem is purely based on, okay, concept is based on Boyle's law. Concept is based on Boyle's law. What is Boyle's law? Pressure is inversely proportional to volume, temperature remains constant. Pressure is inversely proportional to volume and temperature remains constant. So, that is why what we can do here is, that means product of pressure into volume is equal to constant we can take. So, V1 is equal to P2 V2 because the temperature is remaining constant. So, he is saying that if the pressure increases by 1% means I will assume that let P1 is equal to 100 atmospheres and P2 is equal to 100 plus 1 atmospheres because it is increasing by 1%. So, I will take 100 plus 1. Then initial volume, let V1 is equal to V and V2 is equal to V liters you can take. V2 is equal to question mark. That means we have to calculate the final volume. So, P1 is 100, V1 is V is equal to, that is you can take P2 is 101 into V2. So, therefore, V2 is equal to 100 by 101 liters we got. But he is asking you the percentage decrease in the volume is. Percentage decrease in the volume means we have to apply the formula, that is percentage decrease in volume is equal to V1 minus V2 divided by V1 into 100. My dear students, so let us substitute this value here. So, let V1 is equal to, already we have taken V1 is equal to V, I am continuing this step. Let me simplify here, that is percentage decrease in volume is equal to V1 is V minus V2 is 100V divided by 101 into, again V1 is V into 100. So, this is going to be, that is 101V minus V is V by 101 into 1 by V into 100, 100 gets cancelled. So, therefore, 100 by 101 percentage is the answer. So, 100 by 101 percentage means, let us go to, that is second option, and not only that, therefore, you can add something here. Therefore, if decrease in percentage of volume is asked, then V1 minus V2 by V1 into 100 is what you need to apply. If increase in percentage of volume is asked, then V2 minus V1 divided by V1, V2 minus V1 divided by V1 into 100 should be taken as the formula. Then similarly, percentage, if increased percentage of pressure, if increased percentage of pressure is asked, then yes, final pressure minus initial pressure, P2 minus P1 divided by P1 into 100. If decreased percentage of pressure is given, this is P1 minus P2 divided by P1 into 100. All this we have to keep it in mind. All this we have to keep it in mind. Decreased percentage of pressure, increased percentage of pressure, increased volume and decreased volume, all four formulas we can apply. So, this is the hint for 11th question. Now, I would like to continue even the 12th question also. So, I am just rubbing off this and I will explain the 12th question also. So, that means the final answer what we got is 100 by 101 percentage is the answer. So, here already we got the percentage decrease in volume, we got it as percentage decrease in volume is 100 by 101% already we got. So, now we will go for the 12th question. I am going to give the hint for the 12th question. 12th one, what we need to do here is for 12th one hint, I want to take the hint for 12th question also. So, 12th one hint, In the van der Waals gas equation, we already know that excluded volume, B is the excluded volume, because what will be the molecular diameter of the helium if the van der Waals constant B is equal to 24 ml per mole, he says. So therefore, what I am trying to say here is that is B is equal to, this is B is the excluded volume for 1 mole of helium, excluded volume for 1 mole of helium. So, but we already have the formula, and that is equal to 24 ml. 24 ml means, if B is equal to 24 ml means, I can just convert, I want to convert this 24 ml to, that is decimeter cube. So decimeter cube means 1 decimeter cube is equal to 0.1 meter of whole cube, which is equal to 10 to the power of minus 3 meter cube, 10 to the power of minus 3 meter cube. So if 24 ml is equal to 24 ml, I'll expand this again, 10 to the power of minus 3 into 1 meter is 10 to the power of 2 centimeter whole square. This is 10 to the power of minus 3 into 10 to the power of 6 centimeter cube, sorry, this is centimeter cube. So this is 10 to the power of 3 centimeter cube. That means 1 dm cube, 1 liter, okay, 1 liter is equal to 1 decimeter cube is equal to 10 to the power of 3 centimeter cube. So if 1 decimeter cube is corresponding to 10 to the power of 3 centimeter cube, and if 24 ml is equal to 24 centimeter cube, then 24 centimeter cube, because 1 ml is equal to 1 centimeter cube you can take using the mole concept, corresponds to how many dm cube. So this is going to be, that is 24 into 10 to the power of minus 3 dm cube. Dm cube means, again I will convert this to meter cube, because anyhow the answer is in angstroms. The answer is in angstroms. So I will just convert this to 24 into 10 to the power of minus 3 into that is 10 to the power of minus 3 meter cube, because 1 dm cube is equal to 10 to the power of minus 3 meter cube. So ultimately this is going to become 24 into 10 to the power of minus 6 meter cube. Why? What is the necessity for me to solve this excluded volume in terms of 24 into 10 to the power of minus 6 meter cube? What is the necessity? So actually the formula for the excluded volume is, now I am giving you the formula, take this formula, because you are calculating the diameter for one molecule of diameter means directly I am giving you the formula. B is equal to that is 4 into N naught into V of the total volume. You know that excluded volume is 4 times the actual volume occupied by the entire gas molecules if the gases are real gas molecules. So that's why now excluded volume, B value already we got, excluded volume for the helium molecule, helium atom we already got it. So that value I am substituting here, 24 into 10 to the power of minus 6 meter cube is equal to 4 into 6 into 10 to the power of 23 into volume I am taking 4 by 3 of pi r cube, 4 by 3 of pi r cube. So r value you will get the answer in, that is x value in angstroms. You can convert this to angstroms, and because he is asking diameter, that is 2 into x, that means this r value, this is only for radius of helium atom. If it is molecule, okay, molecular diameter of helium means if 2 molecules are coming closer, molecular diameter of helium means take two helium atoms like this. When they come very close to each other, this is r of r, something like van der Waals radius. This is van der Waals radius, because the question itself is based on van der Waals radius. So molecular diameter is equal to twice the radius in angstroms, which is equal to, that's nothing but, you calculate, you are going to get 2.66 angstroms. So please select the option, that is second option, 2.66 angstroms. So my dear students, look at this problem here. A balloon filled with the nitrous oxide, is pricked with a sharper point, pricked. Filled with nitrous oxide means this is laughing gas. Laughing gas whose molecular weight is equal to, each nitrogen atomic weight is 28 grams, I mean each nitrogen atomic weight is 14 and there are 2 nitrogens, so 14 to 28 and each oxygen 16, so molecular weight is 44 grams. Okay, fine. So 44 grams we will take. Then is pricked with a sharper point and quickly plunged into a tank of carbon dioxide. Again carbon dioxide also, that means what we are doing, we are taking a balloon. What we are doing is we are taking a balloon. This balloon is actually made up of nitric oxide gas and this is plunged into a tank which contains carbon dioxide under same reduced pressure and temperature. So this is carbon dioxide. This is carbon dioxide. So when this balloon is plunged into carbon dioxide container, of course it is a closed container, but both are having same molecular weights na. So molecular weight of nitrous oxide is 44 grams and even molecular weight of carbon dioxide also it is 44 grams. So I can say that rate of diffusion of nitrous oxide is equal to rate of diffusion of carbon dioxide. So you find that when you are bringing the nitrous oxide into the carbon dioxide container, you still find that because both the molecular weights are same, we can say that neither the balloon is going to enlarge or neither the balloon is going to shrink, but it remains same because the molecular weight is same, so remains unchanged. So that means for 13th question the correct option is third option, remains unchanged. Now go for the 14th one. In 14th what we have to understand here is it is based on the Van der Waals gas equation. You know very well that in the Van der Waals gas equation, hint if I give the Van der Waals gas equation, Van der Waals gas equation if I take, then P plus A by V square of V minus B is equal to RT is the Van der Waals gas equation, and we know the significance of A and B. A signifies measure of liquefiability, A signifies the measure of the liquefiability of the gases. So liquefiability of the gases means, I mean to say, greater is the A value for any given gas, more is the liquefaction. When more is the liquefaction, more is the compressibility. That means we can take A is directly proportional to liquefiability. That means it is greater compressible. When it is greater compressible, its Z value, okay, is inversely proportional. Lesser is the Z value, more is the liquefiability, more is the A value. So therefore, in these 4 options, the table indicates the gas which is most easily liquefiable means we can take the ammonia gas is the gas which is more liquefiable because its value is 3.85 liter square of atmospheres of mole inverse of 2 is what you have to keep it in mind. And if you go for the significance of B signifies the effective size of the gas molecules. Significance is effective size of gas molecules. So therefore, because he is asking about the measure of the liquefiability, ammonia is having the highest liquefiability. My dear students, if you go to the problem number 15, if you are going to take, for example, which of the following mixture of gases is not applicable for Dalton's law of partial pressure. First option, if I give you, so here if you take the options, for example, if I am giving you H2 gas plus carbon monoxide gas plus ammonia gas is one case, carbon monoxide gas plus chlorine gas is not applicable. I said is not applicable means Okay, just let me give you the options. Let me give you the options. Carbon monoxide gas plus N2 gas, and D if you take, that is N2 gas plus O2 gas at room temperature. At room temperature. So, you know very well that not applicable means the mixture of gases which do not have chemical interaction, okay, chemical interaction, okay, are applicable. Applicable means, that means mixture of gases should not have any chemical reactivity. For example, under ordinary conditions you can't expect hydrogen to react with carbon monoxide. Carbon monoxide also will not react with ammonia. So, it is applicable. So, first option is not correct. Carbon monoxide and chlorine gas, they are very poisonous. So, they directly react under ordinary conditions in the presence of sunlight to give a very poisonous compound COCl2. So, chemical interaction is there, 100% chemical interaction is there. So, this option B is not applicable for Dalton's law of partial pressure. Next, of course, carbon monoxide and N2 gas also, they do not have any chemical interaction, and nitrogen and oxygen also under ordinary conditions they will not react because they are chemically stable molecules. So, therefore, only option B is correct when you speak about the chemical interaction. Now, suppose one more point what I would like to give here is 16th one. Which among the following cases have high volatility, which among the following cases have high volatility, and that is high volatility. High volatility means that is quickly evaporating and low solubility. Suppose I am taking A here ammonia, B phosphine, C we can take water, D acetic acid. Very simple question. What we need to understand here is, we are saying high volatility and low solubility, but one thing what you need to understand here is, for 16th question, that means what you have to understand here is volatility is directly proportional to increased vapor pressure. Volatility is directly proportional to increased vapor pressure and inversely proportional to hydrogen bonding and inversely proportional to solubility. This you need to keep it in your mind. Also, if you take non-volatile nature is again directly proportional to decreased vapor pressure, directly proportional to hydrogen bonding and directly proportional to solubility. That means there is only one case, one option in the 4 options whatever I gave, there is only one option which does not have hydrogen bonding. Ammonia has hydrogen bonding, water has hydrogen bonding, and acetic acid also has hydrogen bonding, but only phosphine is the only hydride of that is Nicogens P block group, 15th group, wherein which it does not have any hydrogen bonding. If it does not have any hydrogen bonding, yes, it has high volatility, volatility increases, vapor pressure increases, then when volatility is increasing, vapor pressure is increasing, hydrogen bonding and solubility decreases. So, therefore, we will go with the second option. So, my dear students, whatever is the best possibility is there for states of matter, I have covered each and every case in the states of matter, each and every topic whatever I have given you, whatever I have explained in topic wise, to give you the extra edge and extra advantage, I have actually stressed the concepts in topic wise, topic 1, topic 2, topic 3, like that. You can refer the concepts whatever I have explained, and in the numericals also I tried my level best to give you variety of different questions. Almost I've given you some 15 numericals I've given you of different models covering all the topics in the states of matter, but however there are few topics because of the time constraint maybe I could not stress, because there's one unit in states of matter where properties of liquids also it is included in this unit, but that topic again anyhow you are going to learn in that is solutions. In second year solutions లో మీకు ఆల్రెడీ ఆ టాపిక్ ఉంటుంది కాబట్టి అది ఇక్కడ డిస్కస్ చేసినా చేయకున్నా మీకు మళ్ళీ అక్కడ వస్తుంది కాబట్టి ఆ ప్రాపర్టీస్ ఆఫ్ లిక్విడ్స్లో అక్కడ ఉన్న ఫార్ములాస్ అవన్నీ కూడా మీరు అక్కడ మళ్ళీ మీరు ప్రాక్టీస్ చేసుకోవడానికి అవకాశం ఉంటుంది. బట్ ఇక్కడ నేను మ్యాక్సిమం వాట్ ఎవర్ ఈస్ పాసిబుల్ ఫ్రమ్ మై సైడ్ ఐ గివెన్ యూ ఆల్ ద ఇంపార్టెంట్ న్యూమరికల్స్, very important numericals. I tried my level best to discuss, and based on this I am confident that all of you are going to get benefited from whatever the explanation I have given you for the states of matter, and I wish you all the best for the coming entrance exam, whatever the exam you are writing, whether it is EAMCET 2017 or IIT MAINS 2017 or NEET 2017. I wish you all the best.